So in this video, we're going to start a new unit on problem solving, and we're going to be especially talking about different models that we might use. So in general, we talk about math models. It's just a way to study or predict what might happen to try to solve different situations, try to get the best answer possible. And in this lesson, we're going to look at three types of models that we might see. The first one is a numeric model. It's when we look just at tables of data perhaps, and from that table try to get some answers. We'll do a little bit of this in this unit, but most of it will be the second two types of models. So if we were just to look at this opening example here, it says the numbers in the table, they show the growth of the minimum hourly wage from 1955 all the way to 2005. And then on the right side, they show us the minimum hourly wage that's been adjusted to the purchasing power of, and they just picked the $1996, but basically if everything was standardized, what would be the year where we could buy the most with our money? And just from looking at that, we could answer these three questions here. So part A says, in what 5-year period did the actual minimum hourly wage increase the most? So for this one, you're just going to be kind of looking at the jumps from year to year here, and you're going to find that from 1975 to 1980 it increased by $1, and that's the most out of all those years. Part B, in what year did a worker enjoy the most purchasing power? So again, you have to read the question and know where to look. In this case, we're going to look on the right column and just looking for the biggest number here. So in 1970, it looks like we had a purchasing power of $6.47. So even though the jump was biggest right here, we actually had the largest purchasing power in 1970. Part C says a worker on minimum wage in 1980 was earning nearly twice as much as a worker on minimum wage in 1970, yet there was great pressure to raise the minimum wage once again. Why is that? So you can go ahead and look at your table and just try to come up with an answer for that. But we would end up looking at the purchasing power. In 1980, we could buy something that was worth $5.90 in 1996, and in 1970 that was up to $6.47. So even though they're earning more, the purchasing power dropped. The factor of inflation actually made money not worth as much. And so that'd be an interesting kind of history lesson there, what was going on in the country around that time. But going through a recession, your money's not going to be worth nearly as much. So that's basically just what a numeric model is. It's kind of mathy, but more it's just looking at a table of data and trying to answer questions from it. An algebraic model is probably the type that we'll use the most in this unit. So we're going to try to build a function or build an equation relating different variables that's going to help us figure out the answer to a question. The textbook likes to use this term phenomena. What phenomena is being studied? How can we answer a question based on that? So this is a very simple example using area. Let's say that we're going to buy a pizza. We could either get a rectangular pizza, maybe from Jets, or we could get a round pizza, maybe from Pizza Hut. And we know both pizzas are the same thickness. Which option would give us the most pizza for the money if they're the exact same price? So this really boils down to area. If they're the same thickness, all we're going to be worried about is the kind of the surface area or the top area of the pizza. And in that sense, then when we incorporate the same thickness, we'd be talking about volume of pizza. So in no way is this related to the taste of the pizza. It's simply, I want the most pizza I can possibly get. So we need to come up with area formulas. So we might start just by drawing a picture. We know that one is 20 inches by 22 inches. The other one has a 24-inch diameter. And so we need to think about how we would find the area of both of those shapes. So a rectangle is length times width. You go 20 times 22, you get 440 square inches. For a circle, it's pi r squared. So we know the diameter, we need to take half of that. Pi times 12 squared, we get 452 square inches. So the round pizza is a better deal. And our last example is going to be a graphical model. Many ways that we could use this. Sometimes we simply take data from a chart and we graph it, try to see what that helps us visualize, helps us see. Sometimes we'll take an algebraic model and graph it and see what that might tell us. So it's somehow using these two types of models just to look at things from a different perspective. So famous scientist Galileo, he was interested in what happened as you just rolled a ball down a plane. How far would it go, and what was the distance at certain times? So he maybe collected this data here. So at 0 seconds it hasn't gone anywhere, but at 4 seconds it had already traveled 12 inches, and tried to figure out if there was a pattern to this. So we could go ahead and enter this into our calculator if we wanted to, get a stat plot, and it sure looks like there's a lot of varieties here that we've been talking about, but perhaps a parabola would be one that we thought of. It looks like it could be a parabola or a type of power function, maybe an exponential function, some other things that we've talked about. And we could go through this and find a model that fit. Maybe we could do some sort of regression. In this case, it's going to fit perfectly. So we could even just test some things with numbers here and might come up with a pattern, but it'd be 0.75 times t squared times time squared. Most of the time that we're doing this, we probably want to get the exact numbers to match up like it did here. So just something to be aware of. It's really related to regressions in this case, but we could also look at some graphical ideas just from a function in general that we had to build and get some answers from that. So now using the regression that we have, we could answer things like what's going to happen at 10 seconds, or when will it have traveled a distance of 100 feet, things like that. So just to kind of give you maybe for tougher questions an idea of how to solve problems, this is something that I think a famous mathematician kind of wrote out at one point. I'm just going to call it a general problem solving process. 4 steps. First of all, just understand the problem. Read it. Just make sure you kind of get the big ideas. If it's confusing, maybe try to restate the problem. Once you've done that, draw a picture. A lot of questions, a picture will help you get a sense of what's going on here. Figure out exactly what you're trying to find and name a variable for that. And then try to come up with some sort of equation or inequality or some sort of rule that you know from your previous math courses that would relate your picture and this variable together. Okay, once you've done that, then actually solve for your variable. So use one of the models that we've been talking about in the video to do that. If you can, try to solve it a second way, although a lot of times we just maybe would take our answer and plug it back into the original. But sometimes there can be more than one way to look at a question. And then once you've done that, since a lot of these are going to be applications, tell me what that means. So if x equals 20, well, what, 20 what? What did x stand for in the original problem? And then decide if that would actually make sense. So we're just going to go through one of those right now, and maybe a little tougher than the first 3 that we looked at. So let's pretend that you are installing a window and you have a 20-foot ladder. You want to make sure it's nice and stable so you don't fall down, and you are told that it's going to be stable when the distance from the base of the ladder to the base of the wall is 4 feet less than the distance from the base of the wall to the top of the ladder. And so in this position, with this 20-foot ladder, how far up the building does the ladder reach? So you might have to read through that a couple times, kind of make sure that the general idea makes sense. Make sure that you've looked through, you've thought about it a little bit before you start jotting stuff down. Maybe even restating some of the tougher portions of this. I think that middle sentence is a little tough. But then we want to try to visualize what's going on here. So we might try to draw a picture. So we have a house. We know something about having a ladder that's going to lean up against the house. We know the ladder has to be 20 feet. At this point, you might say, well, I want to know the distance that it's going up. I want to know from the base all the way up to here. So maybe I call that x, and I would maybe even label that in my question. X is the distance up the house that the ladder would reach. So if we call that x, the question also tells us that the base part has to be 4 feet less, so that'd be x minus 4. And then if we think about that, we have this nice right triangle here. Well, in your math courses before taking this class, you've done a lot of things with right triangles. Pythagorean theorem is going to be one that hopefully jumps out at you. You've maybe done some trigonometry, some right angle trigonometry, some other things that we could think about, but here Pythagorean theorem would probably make sense. If I set that up, I would get x squared plus, and then x minus 4, the base of that triangle being squared, is going to equal 20 squared. And if our job is simply to solve for x and you have a calculator handy, at this point you could actually type in this side into y1 and this into y2 just as it is, and you could solve using intersections so you could figure out what x was. If you don't like that, you could simplify for a little bit. So if I were to actually put the entire left side together, if I FOIL x minus 4 times x minus 4, figure that out, add an x squared in there, I would get this statement, and 20 squared is 400. So again, if you would rather type that into your calculator, you're going to get the same picture in the end. But again, you could solve that with intersections. If you don't like that, or for some reason this was a no calculator question, you have to do a little bit more. So maybe we would set one side equal to 0. And now if you had to graph it, you could solve with x-intercepts. You could, because it's set equal to 0, you could use the quadratic formula. If there was no calculator, this one is possible to solve through factoring. It'd be a little tougher, but you could do that. But regardless, any of these 3 steps here, you are able to get an answer. And what the calculator would give you would be 16 or negative 12. So you've kind of gone through step 1, step 2, and step 3 in that problem solving process. Now we need to interpret our answer. Well, because we're talking about a length of negative 12 doesn't really make sense. 16 I think would. Okay, and if we wanted to verify that, we could go ahead and say if this is 16 and this was 12, right, because it's 4 feet less, and this is 20, would that fit back into the Pythagorean theorem? Would that actually work out? We could go through and test that and verify that it would. So in the end, the answer for this question is 16 feet. It's a little bit more of a more challenging question, and we will look at even more challenging questions in some of our homework assignments for this lesson. So jot down questions, and we'll see you in class.